In the initial phase of modern compilers, lexical analyzers process continuous streams of source code. They ingest raw text, rapidly breaking it into meaningful components. The engine driving this rapid processing is a deterministic finite automaton, or DFA. These act as high-speed, state-based pattern recognizers. We generate these DFAs automatically by converting regular expressions. The math guarantees a working recognizer, but the conversion process often generates dozens of redundant, extraneous states. Every excess state forces the compiler to allocate additional memory and burn extra compute cycles. When evaluating millions of lines of code, this state bloat creates measurable processing friction. We resolve this through a mathematical process called DFA minimization. It is a mandatory step to strip away structural redundancy. By isolating and identifying states that exhibit identical mathematical behaviors, we can reduce an automaton to its optimal form. Once the mathematical foundation is established, we can examine how tools like Lex operationalize this theory into executable software. To build an efficient compiler, one must master both the mathematics of state reduction and the programmatic tools built to implement it. The rule of DFA minimization is absolute. We must reduce the total number of states without altering the language the automaton formally accepts. We achieve this by evaluating a single core metric, state distinguishability. We determine if two states are distinguishable by feeding them a sequence of future input strings and observing the results. Here is a scenario with two separate states, B and C. Tracing the input sequence 1, then 0 from state B leads to an accepting state. Tracing that identical 1-0 sequence from state C terminates at the exact same accepting state. Mathematically, if every possible future input leads two separate states to the same outcome, either both accepting or both rejecting, those states are indistinguishable. Indistinguishable states are logically identical. Maintaining them as separate nodes in our graph serves no purpose. They must be merged. To globally minimize an entire DFA, we rely on a formal three-step partitioning algorithm. On the left is an unoptimized DFA. On the right, a blank partition table. Step 1 is initial separation. We divide all states in the graph into two fundamental sets, based solely on their final status, accepting states and non-accepting states. Step 2 is checking distinguishability. We iterate through each set and test the transition destinations for every possible input character. We evaluate the transition of the non-accepting states on input A and then on input B. We look for an anomaly, two states starting in the same set but transitioning to different sets on identical input. This divergence proves the states are mathematically distinguishable, so we split the partition into smaller subsets. We repeat this check recursively across all groups until no further states can be split. Step 3 is construction. Our stabilized partition groups form the definitive single states of our new machine. We recalculate the transition edges to connect these newly merged states, resulting in a streamlined automaton. This strict deterministic algorithm ensures the resulting machine uses the absolute minimum memory footprint required to recognize the language. Graph theory provides the rules, but practical software engineering requires automation. Manually calculating partition tables for complex programming languages is impossible at scale. This is why compiler engineers rely on Lex. It is a lexical analyzer generator designed explicitly to automate this mathematical pipeline. Instead of drawing nodes and transition arrows by hand, engineers write declarative rules using standard regular expressions. First, engineer rules are saved in a .l file and fed into the Lex compiler. The Lex compiler calculates the minimized DFA and generates an intermediate C program, lex.yy.c. Finally, a standard C compiler takes that file and compiles the final executable scanner. Lex serves as a bridge, converting abstract automata mathematics into an automated build tool. To use the Lex tool, engineers format their input file using a three-part architecture. This schematic details the internal layout of a standard .l file, separated by double percentage markers. Section 1 is for definitions. This block handles C-level header inclusions and declares any structural variables the analyzer will need. Section 2 holds the rules. This is the core engine block, where declarative regular expressions are directly paired with executable C code actions. For example, an engineer can write an identifier rule so that matching a specific alphanumeric pattern triggers a pricked command or returns a value. Section 3 contains user programs. This is reserved for auxiliary helper functions and the vital main driver function. That main function relies on ylex, the generated engine block, that actually initiates the scanning process and executes the underlying DFA. This three-part architecture maps high-level pattern matching logic directly to low-level execution triggers. This master pipeline diagram maps the journey of lexical analysis from start to finish. We begin with a simple regular expression. Internally, the compiler converts that expression into a non-deterministic machine, or NFA. It then determinizes that NFA, creating a functional but likely bloated DFA. We apply the three-step partitioning algorithm, collapsing the state graph to calculate the absolute minimal configuration. That minimized mathematical model is then implemented through the Automata Lex toolset. The final output is the compiled executable scanner, yielding discrete tokens for the parser. This progression marks the transition from abstract state reduction to a functional automated pipeline for source code analysis.